In lesson 1.2, we pointed out that current is the flow or the movement of electrons, or of charge, along a conductor. When charge moves along a conductor, there are electric and magnetic fields that are generated by that charge flowing through the wire. There's an electric field that radiates away from the conductor, and there's a magnetic field that circulates around the conductor and also radiates away. Now, if current is the movement of charge and a signal is a point concept, and by that what I mean is there is a signal at this point on the conductor, and then that signal propagates along the conductor. So the little component of charge associated with that signal also propagates along the conductor. So current is the movement of charge, a signal is a point concept, and here's a picture of a signal propagating along a trace. Well, at a specific point in time, that charge can couple into an adjacent trace. And since like charges repel, then charge moves away from that point on the adjacent trace. We have a little component of charge that is propagating along this trace. That's the signal. That little component of charge right at this point in time repels like charge away from that point on the other wire. So we have a little component of charge that moves away in this direction. We have a little component of charge that moves away in that direction. Well, a component of charge that is moving is a current. And so what we have is we have a signal that is propagating along this trace, can couple into an adjacent trace. That little charge can couple into an adjacent trace and create a current in the adjacent trace that flows away from it in both directions in this particular case. We call this electrical coupling, charge coupling, or capacitive coupling. These are all, from a practical standpoint, the same thing. Different people sometimes refer to it different ways, but it's all the same thing. Capacitive coupling of charge on one conductor coupling into another conductor. Now, also, if we have a current flowing out of the screen on a conductor right here, there'll be a magnetic field around that conductor. If we have an increasing or changing current on this conductor, then we'll have a changing magnetic field. A changing magnetic field around this conductor couples into an adjacent conductor and induces a current flow into the screen at this point. That represents Faraday's law. A changing current in one wire induces a current in an adjacent wire, and that's Faraday's law. And that's the principle behind a generator and a transformer. And we call this magnetic coupling or inductive coupling. Again, from a practical standpoint, those two things mean the same thing. So, collectively, these fields are called the electromagnetic field that radiates away from the wire or the conductor. And the magnetic field, the electric field, and the current flow are all inseparable. And what I mean by that is the magnetic field can't get out in front of the electric field can't get out in front of the magnetic field, and neither one of them can get out in front of the current flow. They all propagate together at the same time down a conductor. Now, electromagnetic field radiation is neither inherently good nor inherently bad. Now let's look at a couple of illustrations. Here we have a signal that couples into an adjacent trace. Well, that's bad if that coupling results in crosstalk. But if this happens to be a differential pair, well, then it's good because differential pair coupling is actually beneficial. If this is a wire or an antenna that is radiating away to another antenna out here somewhere, well, that's bad if that other antenna happens to be at an FCC compliance testing range. But if this antenna happens to be in your watch or your tablet or your radio or your television or your cell phone, well, that's good because that's a form of communication. So we as engineers and board designers have the responsibility of trying to optimize the beneficial radiation and minimizing the bad radiation from the electromagnetic energy and the electromagnetic fields. But the electromagnetic fields themselves are neither good nor bad. It just depends on the situation. Now, in the next few slides, I'm going to show some illustrations of the electromagnetic field. These were generated using the Hyperlinks signal integrity tool and signal integrity simulator. And the reason I'm going to go through this is because from a board design standpoint, it is helpful if you can visualize what is happening to the electromagnetic field. And I'm going to illustrate that in several different ways as we go along. In this first illustration, we're going to look at the difference in height above the plane. Here we have an 8 mil trace, 50 mil height above the plane, and a 50 mil separation from adjacent traces. And here's what the electromagnetic field around that trace looks like. And it's all over the place. It's out in the air, it's radiating out to these other traces, and so on. Here's exactly the same thing, except it's a 5 mil height above the plane instead of 50. And look at what happens to the electromagnetic field. It goes from here to here. And when we get down close to the plane, it's almost completely trapped between the trace and the underlying plane. Think EMI when we think of something like this. Here we've got radiation out in all kinds of directions. Here the radiation is pretty well contained between the trace and the plane. Microstrip versus strip line. Here's a microstrip situation. We have 8 mil traces, 50 mil separation, and 10 mils above the plane. Relatively close. But here's what the electromagnetic fields look like. In a strip line configuration, we have the same thing. 8 mil traces, 50 mil separation, 20 mil between the planes, and so 10 mils on each side of the trace to the plane. And look what happens to the electromagnetic field in this situation. It's completely contained between the planes in the strip line environment. There's no electromagnetic radiation that is getting out to the outside world. Here, there's a little bit of radiation getting out to the outside world. Again, think EMI. Now, I want to make the point here that this does not prove that you can't get good EMI performance from microstrip. You certainly can, and we do it all the time. Nevertheless, the fields are even more tightly contained in a strip line environment. And so the strip line environment can be beneficial from an EMI standpoint. This is an interesting case where we look at the impact of trace width. Here we have an 8 mil trace, 5 mil height above the plane, and we can see what the electromagnetic field looks like around that trace. Now here's an 80 mil wide trace with the same 5 mil height above the plane. And look at the difference of how much of the electromagnetic field now is captured between the trace and the plane, with just a little bit of it radiating out into space compared to the narrower trace. Now, the impact of that is going to show up in propagation speed. The speed with which a signal can travel depends on the environment that the electromagnetic wave is in. In this case, approximately half of the electromagnetic wave is in the dielectric, and approximately half of the electromagnetic wave is in air. And the signal, or the wave, propagates a lot faster in the air than it does in the dielectric. Well, here, most of the electromagnetic field is in the dielectric, and very little of the electromagnetic field is in the air. So, in this case, the signal is going to slow down because of where the electromagnetic field is. So just by looking at the electromagnetic field, or thinking about where the electromagnetic field is, we can make some inferences about things like the propagation speed. How about the impact of separation? Here's two 8 mil traces, 5 mils above the plane, with a 5 mil separation. The electromagnetic fields are coupling these two traces together pretty well. Here we separate the traces by 25 mils instead of 5. And now a lot of the electromagnetic field is captured between the trace and the plane, and much less is interacting between the two traces. Think crosstalk. Here we have a lot of opportunity for crosstalk coupling. Here the crosstalk is much less because the traces are a lot farther apart. Impact of scaling. Here we have an 8 mil trace, 8 mil separation, 5 mils above the plane, ½ ounce thick trace. Here we have 16 mil trace, 16 mil separation, 10 mils above the plane, and 1 ounce thickness. And look at the electromagnetic fields. In fact, you might think that I've made a mistake here and just repeated the same figure twice, because the electromagnetic fields look virtually identical. The only clue that that's not true is by the thickness of the plane. When you look at the plane here and you look at the plane here, now you see that this really is scaled differently. But the electromagnetic field is the same. Interestingly enough, the impedance of the traces is the same in both cases too, which illustrates that the impedance of the trace is not so much determined by the dimensions of the trace, it's determined by the distribution of the electromagnetic field. If we scale everything up from here to here, but we scale everything up, we don't change the electromagnetic field, therefore we don't change the impedance. So you can gain quite a bit of insight by thinking about what the electromagnetic field looks like when you are designing your board or considering changes maybe to a board or considering alternatives. Think about where the electromagnetic field is, think about what the impact the change will have on the electromagnetic field, and you can gain a lot of insight about what's going to happen. So, the takeaways from lesson 1.4. The electromagnetic field impacts things like EMI and propagation speed and crosstalk and impedance and lots more. If we think in terms of where the electromagnetic field is when thinking about signal integrity issues, we gain quite a bit of insight into what is going to happen from a signal integrity standpoint.